Okay, Shabab, I welcome you. I don't know. It could be one lecture today, and then we go we go home, or it could be a series of lectures. Inshallah, will you benefit from it, and I benefit from your challenging questions, so that some things can be beneficial. So, the idea of this series of lectures is really to highlight those unifying ideas that have defined modern physics. Classical physics in the past was mostly modern physics. They're not many, but the few that they are very beautiful, they're very deep, okay? But they have required a lot of effort from a lot of very bright people. So it's not something that you can catch on the fly. It's something you have to sit down, think about it, and really appreciate it in a sense. So it's not something that is trivial at all. Okay, so probably the most important idea in this context is the idea of action and the principle of least action that comes with it. This idea really is actually is part of a bigger problem. We call it the variational principles. And as applied to our physical systems, it takes the form of what we call the principle of least action. This is just one case. It's not the only one. There are other ones. It's how to define the dynamics of a system, okay, given certain quote unquote boundary conditions. Okay. So everybody is familiar with the action. So let's define the action and move from there. So let's start a little bit low and then we go out. Let's assume we work in one dimension only. Okay? Just one dimension. And my system, it could be one particle in this case, just one microscopic particle. Okay? At some time T1, it's in position x1, and at some later time T2, it is at position x2. Okay? And then in between, there is some path in between. Okay? Now, I can join these 2 points by many paths, but all classically, huh? But classically, only one of them actually is realized in nature classically. Okay, and this we can actually put it into mathematical terms. Okay, by doing the following: we define. Let's say this is what we call here. Okay, so this is what we call a virtual path. Okay, and it's a path that is only in your mind. It's not a real one. Okay, and this is the actual path, actual physical path. Okay, now we define something we call the action. And we give it the symbol S, not A, S. No why. Okay? This action is what we call a functional. So what is a functional? Okay, you know what a function is in mathematics, huh? A function is some relationship that gives you from any given number gives you another number. Okay, that's a function. A functional is something that associates a number with a function. Okay, if you have a function, it gives you a number. So if you change the function, you get a different number. That we call a functional. Okay, and usually how the way we write it is this way. So this is the function of some, in our case, a path x of t. So s of x of t is a number. The number that depends on the path that is taken by my classical particle. Okay? Now we define it to be, so it could be definition if you want. Okay? So first of all, well, here it is. In the simplest case, okay, it just what you call L is the Lagrangian. Everybody knows what the Lagrangian is. Okay, in classical mechanics, the Lagrangian L of a function x, variables x and x dot. So x is the position of the particle on the path, that's x. And x dot is just the velocity in this case, okay? So this is equal to, okay, t, kinetic energy, minus, which is a function usually of x dot, minus v, usually it's a function of x. But it doesn't have to be, okay? It doesn't have to be a function of x dot only. Okay, so I'm gonna remove this. What is it? Yeah. Okay, just write it as t minus v. Okay. Now, what is this action? As I said, it's a number, and we chose it in such a way that it is linear in the sense that if you double the path, you double the action. Okay. If you reduce the path, the action is also reduced accordingly. So it is linear, if you want, in the path length. It's linear in the path length. This is one feature of it. Okay, so it has to be linear, okay, in the path length. So that if you double the path length, you double the action. Okay, so I can break it into small segments. Okay. Okay, and then for each one of them, I define an elementary element of action delta S. Okay, and this will be L delta T, if you want. Okay, so if I increase delta T by 2, delta S is also increased by 2. So that's the first feature. Then, now, so let's do this. For the very simple case, one dimension, Cartesian coordinates, okay? So what we have, T is what? For a particle of mass M, what is it? Yeah, M x dot square. And then V is a function of x. Well, we all know what the equation of motion should be. That's Newton's equations of motion, right? Okay? So let's try to derive it from this formalism. So the condition we impose on S is that the variation in S is 0. And that's what we call the principle of least action. Well, it's mostly least, but not always least. Sometimes it's most. Okay, what we impose is that S should be stationary or should have an extremum. What does it mean? It means that the first order change in S as I change the path is 0. Okay? If I change the path, the first order change in S should be 0. Around the classical path, around the real path. So the changes will be second order and higher. So it's like the minimum of a function. Remember? The minimum of a function is defined by having the derivative equal to 0 at that minimum or maximum. Right. So what is delta S? So if I have a path like this and the nearby path, this thing here I call delta X. Okay? So my action now on the nearby path is this much. Okay? And I subtract from it the action on the actual path x of t. Okay? What is this? Okay? Let's substitute. So what is this? This is equal to the integral, the Lagrangian here, what is it? 1/2 m x dot plus delta x dot square, okay, minus v of x. So that's the x plus delta x, okay. dt minus the integral 1/2 m x dot square, all right, minus v of x dt. And I require that this change should be 0 to first order in delta x and delta x dot. Okay? طيب, if I look at this, what do I get? So delta s is equal to what? What do I get from here? Only one term will survive, huh? I'm keeping terms in first order in delta x and delta x dot. Don't forget that. So this delta x dot square, I forget about it. Okay? So what do I get? I get the cross term only. The other term is just cancelled by this one. So I get m, so the integral of dt, m, x dot delta x dot. And then here what do I have? I expand this in Taylor series. First term cancels this one. I'm left with the second one, which is minus delta x, partial v partial x. In this case, it's one term only, so plus higher order terms, which I said I don't worry about. I don't want them. I keep only to first order. Okay? Fine. And I require this to be 0. Yes, sir. Please ask question anytime you want. Yes. I'm looking at infinitesimal changes. So delta x and delta x dot are extremely small. Okay? And in the end, I go to the infinity or it is 0. So all the other terms will cancel out. The term that I'm left with will have no delta x and no delta x dot, but all that have delta x and delta x dot will cancel out. Okay? It's a usual trick we do. Type. Now, delta x dot is delta dx dt, right? This I can write as d dt delta x. Okay? In physics, we can always do that. Okay. But it's true, you can prove it, it's not a problem really. It's true, rigorously true. Type. So, this is my delta S then. M x dot d dt delta x minus delta x partial v partial x. I want to get this delta x and this delta x out of the brackets. So what do? I have to integrate by part. But in doing so, I have to keep in mind that delta x at T1 is delta x at T2 is 0. That's the condition I impose. You see, they start from the same x and they end at the same x. Okay? Okay. So with that condition, then the integration by part just consists into changing the sign and switching the derivative. Okay? So delta S then minus, I will have now m x double dot, and I will have delta x also. Then I can take them out now because the same delta x, just take them out. And so minus partial v partial x delta x. Any questions? So you see Newton's laws coming up, and this has to be 0 for any delta x. What does that mean? That means that the thing in bracket has to be 0. Okay, and therefore I have mx double dot is minus partial v partial x. That's my force. That's my acceleration. That's my second law of Newton. In a very, very simple case. Okay? So my formalism now is equivalent to Newton's laws of motion in a way, because I can get Newton's laws from it. But why don't we just stick to Newton's laws? Why do we need to go to the action and principle of this action and all that stuff? Why is that? It's more general. In which way? Yes? It is scalar quantity. That's okay. It's good to work with. Yes. It can be applied outside. In a way, that's what he's saying. It's more general. Yes. Newton's mechanics needs to know the, yeah. You need to know the forces. That's true. Here you don't need to know the forces. You're right. And actually, when Lagrange wrote his book called Mécanique Analytique, Analytical Mechanics, he said, I finally could solve any problems in mechanics without using any forces. It's a big relief, really. Yes, it's true. But there is one reason also, which now we know it's important. I assume you all had some relativity, right? There are two postulates in special relativity. One of them is, what is it? Constancy of the speed of light. Okay, that's okay. But what's the other one? The laws of physics should be, yeah, should look the same. What does it mean? What does it mean? What does it mean the laws of physics should look the same in all inertial reference frames? What does it mean? They should be frame independent, huh? The form of the law should be frame independent. Are Newton's laws of motion frame independent? When I write F, now we talk about conservative forces, huh? Forget about dissipation and all that stuff. Just conservative force, I mean gravitational, electromagnetism and all that stuff. So if I write this thing, what is it? Right? Or if you want, minus the gradient. I assume you're all familiar with the gradient. So this is a generalization of this equation to 3 dimensions. What is something like this? Am I using a specific frame? I'm using the Cartesian reference frame. Cartesian. That's what this equation is. This is a Cartesian. Because if I use Cartesian, yes, that's true. I will have 3 equations. Fx equals m x double dot. Fy is m y double dot. Okay, and z is m z double dot. But if I have a rotating, let's say, just 2-dimensional rotating frame. I mean, x, not rotating, but r theta frame. Is this true? It's not. It's not true. It's not true. If you don't believe me, if I write this equation for the r theta, I go from xy to r theta. In r theta, the equation doesn't look like this. I have to invent a new force. What is this new force? I have to invent a new force. Centrifugal force, right? Yeah. I have to invent a new force called the centrifugal force. I cannot write this. Okay. So, Newton's laws, when you write them, first of all, they have to be an inertial reference frame. Okay? That's one thing. The other thing is, the way they are written, it's assumed that it's a Cartesian reference frame. Cartesian reference frame. But it's not good. If the laws of physics have to look the same and should be frame independent, that's not the formalism to use. Now here, in this formalism, can be generalized very easily. Here I give you an example for one dimension using Cartesian coordinates. But I can generalize it very quickly. Okay? So, first of all, instead of x, we define a quantity we call q, called generalized coordinate. It could be your r or your theta, for example. Okay? For x dot, I put a q dot, called generalized velocity. And my Lagrangian then will just be q dot, function of q. And now for q, I could have many q1, q2, q3, etc. As many as you need to define your system. Okay? And this should be independent. Otherwise, you have to have, if they're not independent, you have to have constraints, and that's something else. You're not worried about that. Okay? So this is the Lagrangian. This could be r dot, theta dot, for example. So what will be my action then? Now my action now is a function of q of t. What is it? Well, here it is. And I'm assuming for the time being that my Lagrangian does not depend explicitly on time. Okay? It adds a little complication, but essentially everything is the same. Okay? Now what do? I do exactly the same thing. Okay? Exactly the same thing. My delta S now is what? Is delta, the integral from 1 to 2, L q dot dt. Okay? So this, take the delta inside. You can always do that. The integral from 1 to 2 delta L q dot dt. No. L is a function of q and q dot. What is this delta L? You learned this, I think, in Math 101 or 102. Okay? So this is, yeah, partial L, partial Q, delta Q. Okay? It's called chain differentiation, right? Plus partial L, partial Q dot, delta Q dot. Okay? And now, my delta S now would be the integral from 1 to 2. So I have partial L, partial Q, delta Q, plus partial L, partial Q dot, delta Q dot dt. Alright? And delta Q dot, again, I write it as before. d dt of delta Q. Same thing. I want this delta Q and this delta Q to come out. So what should I do? Do an integration by part. So what I have to assume here is that delta Q at T1 is delta Q at T2 is 0. This is my constraint. Okay? Now I just switch the time derivative and put a minus sign. So this is equal to the integral from 1 to 2, partial L, partial Q, minus sign, d dt, partial L, partial Q dot, delta Q dt. And this has to be 0 for any delta Q. For any delta Q. What does it mean? It means now minimizing the action is equivalent to zeroing this thing. So These are now my equations of motion. And if I have more than one Q, okay, so this is just for each one of the ith coordinates. Do we know what we call these equations? The Euler equations of motion. And they have the same form in any frame. You don't change. Cartesian, here they are. Okay? Polar coordinates, it's the same. Curvilinear coordinates, it's the same. No matter what. No matter what. And t here is not half mq dot square. That's only true for Cartesian coordinates. T is t, whatever it is. Okay? I'll give you an example. Two-dimensional motion. Okay? So, if my... This is what? Limitation? Yeah, the only limitation, as I said, we are working with conservative systems. For non-conservative system, it's not good to use this formalism, let's put it this way. You have dissipation and friction and all that stuff. Okay, this is for conservative systems, yes. Inertial? Anything. It's true for anything. Anything. Did they ever have to use that the system was inertial or no? No. Okay? These equations, we use them, well, if you have time, the patience, we'll derive from these equations what we call the geodesic equation from general relativity. Same thing. Same thing. Okay? طيب. If I have, my coordinates are r and theta, and therefore I have q dot is r dot and theta dot. What is the kinetic energy in terms of r and theta? Well, you can write it in terms of Cartesian, which is just x dot square plus y dot square, 1 over 2m, and then x is r cosine theta and y is r sine theta. You can do that, it's okay. But then, what do you get for t? Yes? Yeah? Something like that, huh? That's my kinetic energy. And let's assume that v is only a function of r. Does not depend on the angle, just depends on the radius. Okay? So I have how many equations? 2. Okay? So let's do it. d dt partial L partial r dot equal to partial L partial r. What does this give me? Okay? d dt. What is partial L partial r dot? Huh? So it is m r dot. So that's it. This should be equal partial L partial r. What is partial L partial r? Okay? Now, what is L? Let me write this as L and put here minus sign. That's my Lagrange. So this is equal to minus, let me put this term first. So what is this? Partial L partial r. So I get here mr theta dot square minus partial v partial r. So I have mr double dot equal to mr theta dot square minus partial v partial r. That's your equation of motion. What do we call this? That's the centrifugal force. Your mv square over r if you want. Okay? Which is just mr omega square. So this is mv square over r because v is r omega. Okay? And this is your central force. It could be gravitation, it could be whatever. Okay? And the other one, in this case, where v depends only on r. So, let's write it there. So we'll have d dt partial L partial theta double theta dot is partial L partial theta. Okay? What is this? What is partial L partial theta dot? Huh? This is the only term that depends on theta. So it is mr square theta dot. Mr square theta dot. Huh? Huh? This is equal to what? 0. What is mr square theta dot? It's a constant. Excellent. What is it? Huh? Excellent. It's the angular momentum. Now, something I didn't tell you there, I was hiding it. This quantity, partial L, partial Q dot, what do we call this? This we call the generalized momentum or canonical momentum to the variable Q. The canonical momentum associated with the variable Q. Okay? So in our case, this P is not the linear momentum, just call it P. Okay? Yes. What do you mean by what? Canonical? Any standard. Canonical, according to the law. Canonical, standard thing. Or conventional or, okay. So, in our case, what is PR? The canonical momentum associated with R. Okay? It's partial L, partial R dot. What is that? MR dot. Huh? What is P theta? The canonical momentum associated with the variable theta. By definition, it's partial L, partial theta dot. What is that? MR square theta dot. So this equation tells me that P theta is constant. This usually we call L. Some books they call M, some other books. Okay? The angular momentum for a particle that is moving in what does it mean when V depends only on the radius? What kind of symmetry do I have? Spherical symmetry. So for spherical, in this case for two-dimensional motion, you have, okay, angular symmetry, whatever you want to call it, okay? And the angular momentum is conserved. The angular momentum is conserved. And this is just a very small example from a general theorem. Okay, whenever you have a symmetry, there is a conserved quantity that goes with it. In this case, we have a symmetry in theta. Okay? Symmetry in theta. And therefore, because my Lagrangian does not depend on theta. Okay? I change theta to theta, delta theta. The Lagrangian doesn't change. Then there must be a conserved quantity. And in this case, it is the angular momentum. Any questions? Clear? Now, these equations, as I said, they don't depend on anything. I'm not specifying anything. Telling you this is the kinetic energy, this is the potential energy, this is generalized coordinate, this is generalized velocity. I'm not telling you what they are. So it's true in any frame. And that's the beauty of using the action principle. The action is a number. And that number is expressed as a function of coordinates. So if that number is invariant, then the equation I get from those coordinates should be covariant. The equation should be covariant and it has the same form in all reference frames, no matter what. Okay? Any questions before I move to the next one? Yes. Yeah, this is the point I'm coming to, but anyway, yes. Good? Yes, yes. I'm coming to that. Yes, I'm coming to that. This is non-relativistic classical mechanics. Yes. Yes. Yeah. But the Lagrangian is much more powerful formalism than Newtonian mechanics. Okay. Any other questions? Okay. I could show you, if you are interested, how we derive the conservation of linear momentum, the conservation of angular momentum, and the conservation of energy from symmetry. Okay. Should I do that from the Lagrangian formalism, or is it something already known? You saw that already. Okay. So let me move now to relativity. Okay. Now in relativity, and this is the shortest presentation of relativity you will ever see. Okay. Yeah, we talk about the constancy of the speed of light, the invariance of the laws of physics, and Lorentz transformation, and time dilation, and all this nice stuff. But it all boils down to one thing. Okay. In relativity, we talk about events. What is an event? What is an event? Okay. Like when you graduate, that's an event, right? So you need. So an event is defined by a position when it happens and the time when it happens. Anything that happens at specific time, specific place, that's an event. That event could be looked upon by many observers. One could be you standing still. Another one could be somebody traveling next to you going to the moon. Okay? So, for observer A, so this will be XA and TA. For observer B, observer B, this will be XB and TB. And these two will be related, Galilean if it's not relativistic, or Lorentzian if they are relativistic. But this is not our. Essentially, all of relativity, special relativity, boils down to saying that this thing, this is C, the speed of light, huh? C squared, TB minus TA squared minus XB minus XA squared is equal to C squared. Yeah. No, not observer B. Okay. Sorry about this. Just 1 second. Don't get confused here. So there are two events. Event. Okay. So observer A sees two things, two events, XA and XB. Okay. So that's not observed. So XA, no, it's not good. X prime A. Okay. T prime A. So he sees two events. One, XA, X prime A. This could be the birth of some star. Okay. Could be in Hollywood. And this is the death of that star. Who knows where? Okay. These are two time events where that happens. Now observer B, okay, this is the same event, but for him, this is happening at XB, TB, and this is happening at X prime B, T prime B. Clear, huh? Two events. For my coordinates, they're XA, XB, TA, TB. In your coordinates, it's X prime A, X prime B, T prime A, T prime B. And what we require in relativity, all of the special relativity, can be derived from this requirement that no, I want this minus this, so this is TB, yeah, square minus X prime B minus X prime XB square. It's clear, huh? T prime B minus TB and X prime B minus XB. This is equal to, this is called time interval, I mean the interval, space-time. square root of that. Okay? No matter what the other observers happens to be doing. Could be moving very fast, very slow, but in inertial reference frame, okay? Inertial reference frame. These two quantities measured by any observer, or this quantity if you want, this quantity here, is the same in all inertial reference frames. In yours, in mine, in his, everybody who is in inertial reference frame, when he measures that thing, he will find the same thing. If it's 2, some units in your frame, it will be 2 in all reference frames. And that's really what's important in a way in physics. When you measure something in physics, something is physically meaningful if it's invariant, otherwise it's not meaningful. You measure something, you find something. I measure something, the same thing, I find something else. That cannot be physical. It cannot be physical. So this is the only physically meaningful quantity in space-time, at least, in special relativity. Okay? And that's what we call a Lorentz invariant. A Lorentz invariant. Okay? Any questions so far on this? As I told you, it takes some time to show the laws of transformation of Lorentz and all that stuff you can derive from this requirement. You know what? This is similar to the invariance of the distance, or the square of the distance, if you want, and the rotations in the three-dimensional space. In three-dimensional space, the vector is not an invariant. So, a vector, somebody could be the vector pointing this way, somebody could see it pointing that way, somebody could see it pointing the other way around. But what's invariant is the length of that vector. The length of that vector will be the same for all observers, no matter what. So this is some kind of the length of this, what we call now 4 vector, okay? Now we have the spatial coordinates, and we add another coordinates we call the time coordinates. So we don't have space and time, we have something called space-time. Huh? Space-time. And that's why we need to talk about now 4 vectors. And we give them an index which runs from 0 to 3. Okay, where mu could be 0, 1, 2, or 3. And this is equal to Ct and x. Okay? Sometimes we need to put the mu down. Okay? And this is equal to Ct minus x. And actually the way we write it is this. X mu downstairs is some eta mu nu x nu upstairs, where eta mu nu is a matrix, or just a tensor actually, 1, 0, 0, 0, has minus 1 here, 0, 0, 0. Okay? So this is what we call just the metric tensor in flat spacetime. Okay? So, how can I write this in this formalism? Huh? Yes? Yeah. So it tells me that x a mu minus x prime mu x a mu minus x prime minus x a mu, that's invariant, okay? That's invariant. Right? It's an invariant. And it's the same when I put b here instead. It's an invariant. Am I going too fast? Okay? So let me call this delta x. Okay? So delta x mu delta x mu is an invariant. And I give it even smaller. Dx mu dx mu is an invariant. Now the two space-time events are very close to each other in terms of time and space. They're very close to each other. Okay? And this can be written as eta mu nu dx mu upstairs dx mu upstairs. This is an invariant. I mean Lorentz invariant. It does not depend on the reference frame in which you happen to be. Okay? I think we should jump to general relativity from here quickly. What do we have to do to go to general relativity? Okay? This we call ds squared. Now it's a small s, it's not the action, be careful. It's a small s. This is an invariant. This is an invariant. Let's go to relativity first. Now, in relativity, special relativity, I have a free relativistic particle. The simplest case, free relativistic particle. And I ask you, what should my action look like for a free relativistic particle? It's a number. It should be an invariant. And it should be linear in the interval and all that stuff. How many invariants can I make for? Could it depend on the origin of time? Could it depend on the origin of space? It shouldn't, right? Because you can have a different origin than mine. So it should not depend on the origin. So it cannot be x mu. So it should be dx mu. The difference in coordinates, that's an invariant in different reference frames. Okay? But x mu by itself depends on the origin. So the only invariant I have for such a free relativistic particle is this one. That's the only invariant I can construct for the particle. That's the only thing I have. I don't have anything else to work with. Okay? But the problem with this one, it is quadratic in the coordinates. I want it to be linear so the action can scale linearly with the coordinates. So what should I do? Well, take the square root. Have you ever seen something like this? Okay? And that's my elemental action with some constant alpha. Okay? Some constant alpha times something that is Lorentz invariant and linear. Okay? And therefore my action, if my particle goes from point A to point B or from point 1 to point 2 in time space, so my action then for this particle will be the integral from 1 to 2 alpha, okay? And then what? Yeah, the square root dx mu, that's it. Looks pretty, but you don't know what it is, you don't know what to make of it. Okay? So let's write it down. Let's write it down. So this is equal to alpha, the integral from 1 to 2, the square root of c squared dt squared minus dx squared. Now you start to see the light at the end of the tunnel. I want to identify the Lagrangian in order to find the equations of motion. I need to know the Lagrangian. How can I find the Lagrangian? I have to write this as something dt. That dt is multiplied by the Lagrangian. Okay, the action, as you know, is L dt. So I have to get dt out. So that what remains is the Lagrangian. So how can I get dt out? Well, let me get dt out. Okay? So, if I get dt out from the square root, what do I get? Well, that's my action. Alpha dt root 1 minus v square over c square, where v is just dx dt, by definition. That's the velocity of the particle. Okay? And therefore my Lagrangian is alpha root 1 minus v square over c square. That's my Lagrangian. For a relativistic free particle. What is alpha? Well, actually, it's not very relevant what alpha is. But to find what alpha is, conventionally, we go to the non-relativistic limit. We go to the non-relativistic limit. Okay? What do we mean by non-relativistic? And if V over C is much, much smaller than 1, then L is approximately equal to what? Alpha times 1 minus half V square over C square, which is equal to alpha, okay, minus alpha over 2 V square over C square. Oh, I did something. Yeah, this should be C here. There should be C, 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 C. Okay? Now this is a constant. It's really irrelevant. In the equations of motion, if I derive a constant with respect to time or with respect to Q or Q dot, it's 0. It's a constant. So I can ignore it. Okay? It doesn't change anything. That's the case always when you have variation principles. A constant doesn't change anything. Okay? And therefore my non-relativistic Lagrangian, which I know what it should be from the first example. What was it? Just the kinetic energies, huh? Remember? Kinetic energy? So half mv squared. And this should be equal to minus alpha over 2 v squared over c. And therefore alpha is minus mc. Okay? And therefore Lagrangian is minus mc root of 1 minus v squared over c squared. That's your Lagrangian for a free relativistic particle. Question: what is the canonical moment? So what should we do? Well, use the definition. In my case, in this particular case, Q is X. The set of Q's, Q1, Q2, Q3. So the set of Q dots is V. Okay, and therefore my generalized momentum or canonically conjugate momentum is partial L, partial V. And if you do this derivative, you will find that this is equal to gamma mv, where gamma is 1 over root 1 minus v squared over c squared, called the Lorentz factor. That's your moment. That's not usually the way we do it. We do it a more complicated way. But see, this way, very straightforward. Very straightforward. How do we find the energy? How do we find the energy? What's the energy of a particle? Huh? The square over, no, a relativistic particle. In general, what is the energy? In this formalism. There is something related to the energy. It's called the Hamiltonian. Have you heard of the Hamiltonian? Huh? For a free relativistic particle, the Hamiltonian is the energy. Now, if I know the Lagrangian, how can I find the Hamiltonian? Are you familiar with that? Should I just, well, let me just write it. It's not difficult. But the way we define the Hamiltonian. Now the Hamiltonian does the same thing to you as the Lagrange in a way, but the Hamiltonian is a function of Q and P. The Lagrangian is a function of Q and Q dot. Be careful. The Hamiltonian has to be expressed as a function of Q and P, the canonically conjugate momentum. So, and we define it to be usually Q dot partial L partial Q dot minus L. You see? So in my case, this will be, in our case here, V partial L partial V minus L. Okay? Well, I know what partial L partial V is. I know what L is. So what is this? Gamma M V square minus, what is the Lagrangian? It is plus MC root 1 minus V square over C square. Now this gamma is really this thing here. You get it? So I multiply this by this. Okay? This MV square gets cancelled by this V square. Alright? And I'm left with the Hamiltonian, which is the energy in this case, is gamma MC squared. So these are your energy and momentum for a free relativistic particle. Okay? Yes? Yeah, it's MC square, yes. MC square, yes. Yeah. It has to have units of energy. Very good. Any questions? Yes? Yes. Why? First of all, it has to be an invariant, the action. It has to be Lorentz invariant. Okay? This means that it can only be a function of dx mu dx mu. That's the only invariant I can make for a free relativistic particle. That's the only invariant I can make. Now I want it to be linear in the coordinates dx. I want it to be, because I want S to be an additive quantity. So if I break the interval into 1,000 intervals, okay, I have one of them, it should add. Okay, if I double the interval, I double the action. I want that. Yeah, the time or just dx. Okay, instead of dx, I put 2dx. Everything, the time scales by 2 and the space also scale by 2. If I multiply dx, the whole thing by 2, okay, I should get also the action scale by 2. That's only happen if I take the square root. Yes, it is necessary. Yeah, no, it's necessary. It's necessary. Okay? This is how, yes, it's necessary. Any other questions? You know what's necessary? You see, in a way, we are trying to find something that gives me back what I know. And this is one condition. If I don't impose it, I will not get what I want. Okay? Yes, sir. Sorry? Yes. It has to have zero mass. Yeah. It has to have zero. That's the only way it can have all. Yeah. And then I should not use this one. There's another formula, and you get E equal to PC for a massless particle. This is for massive. Mass is not zero. What I did here. If it's zero, you have to be slightly more careful. No, now I want to derive for you, using this principle, another set of equations which are fundamental to physics. We call Lorentz force law. You all know Lorentz force law. When you have a charged particle moving in fixed background of E and B electromagnetic fields, then the force will be subject to something you call the Lorentz force law. Okay? Fine. Now the field is fixed. The background of the field is fixed. I'm not interested in the field. The field is fixed. It's something that you impose. Okay, that's next time, inshallah, we'll see when I let the field change, get Maxwell's equations. Okay, but for now, let's see, the field is fixed. I don't want to change the field. I have a particle moving in this fixed background of the electromagnetic field. And I want to find the equations of motion of this particle. Okay? How can I do that? First of all, you know, or you don't know, I don't know. Usually we use E and B, and the force we get is Q E plus V cross B in SI units. You're all familiar with that, huh? Okay? Now, it's more useful to us. It's not necessary, but useful to us. Instead of using E and B, I use the scalar and vector potential. Are you familiar with this? Okay? So that E is actually minus partial A, partial T, minus gradient of phi, and B is the curl of A. Okay? That's what I mean by that. This A and phi, if I know them, I know what E and B are. So instead of describing my field by E and B, I will describe it by phi and A. Not only that, just like when I go from CT and X, I go to X mu, from phi and A, I go to a 4-vector potential A mu. Okay? And this I call phi over C and A. This is the 4-vector potential, just like I define a 4-vector position. Okay? Same thing. So this phi plays in this A, the same thing that time plays in this X. Now, I ask you, what do you think the action? Now, my action now is made of 2 parts. What are they? The action of the particle and the action of the interaction of the particle with the field. This is another property of the action. It has to be additive. Okay? Now, if I have the fields also are changing, I will have something of the field. Okay? Later on, we'll let this change and we'll keep this fixed SP, and this will be changing. معنى إيش? I have a fixed distribution of charges and currents, fixed, meaning I know them, that's what it means, exactly, and I want to know how these particles now, what are the fields that they create. That's Maxwell's equations. We'll do this next time. But for now, let me assume that the electromagnetic field back is fixed. I know what it is, exactly. A is exactly no, or A and B. I want to find what the motion of the particle is in this background of the field. Now, this is general physics question, by the way. When you have even in general relativity, you have a source and you have a particle and you have a field. Okay? If the particles are fixed, meaning you know what they are, and you would like to know what the field generated from these particles are, these are what we call the field equations. The field, like Maxwell's equations or Einstein equations for the gravitational field. The sources are known. I would like to know the field. No. There's a famous saying by Wheeler. He said, "Give me the source, and they tell you what the fields are." The other way around is if I know the fields, either the gravitational field or the electromagnetic field, and I would like to know how the particles move in this field. These are the geodesic equation, one of them, and the other one is Lorentz force law. Okay? Fine. SP we already derived. Remember? SP, we know what this is. What was it? It doesn't look very invariant this way, does it? It doesn't look like a Lorentz invariant. But if you write it the other way, which way? I think this way. Now you know it's an invariant. Now you know it's an invariant because it's written as an invariant. Okay? I need to know what SI is, the interaction term. Again, we ask ourselves, what are the possible invariants I can make that will give, should be a Lorentz invariant, and it should be linear in the coordinates, and it should be linear in the fields. Okay? Should be Lorentz invariant, should be linear in the field, it should be linear in the coordinates. There's only one. Can you guess what it is? Well, I have this, but this already considered for a free particles, huh? So this doesn't count. I have this. What's the problem with this one? It's invariant, okay? It's not linear in the fields, okay? Or it has another problem because it's not gauge invariant. No good. What's the other one? That's the other one. And that's my guy. It's linear in the field, linear in the coordinates, and it's a Lorentz invariant. There you are. But I have to multiply this by something, by the charge, because if the charge is zero, there will be no interaction. Okay? So it has to multiply by the charge. And that's your ds interaction term. That's it. You see how easy, in a way, it is when you know what the answer should be to get. No, really, this is how we build the theories in physics. Sometimes, yeah, in this case, we know what the answer is, so it makes things easy for us. But it's a guide for us, really. It's a guide. It tells you whether your guesses are meaningful, correct, or not. Okay? But in frontier research, there's no guide. Okay? So, that's my interaction term. Q integral a mu dx. And that's it. You're done. Excuse me. So my total action now, the integral, okay, minus mc squared. Okay, before I do that, let me write down what this thing is. Q a mu dx mu. What is that? Q? Yeah? Phi over c times c dt minus a dx. Okay? So the time components, you know, if you have two vectors, this is a0 b0 minus ab. Okay? So, c and c cancels. I want dt out, huh? That's always the case. So q dt times phi minus a times v. And that's your interaction action, elemental one. So what is your Lagrangian then? Interaction Lagrangian, what is it? It's everything that multiplies dt, huh? So it is q times phi minus av. Or let me write it with the q separate for both. So it is q phi minus q a into v. And therefore your total Lagrangian is minus mc squared root 1 minus p squared over c squared plus q phi minus qa into v. Okay? Any questions? Once I have found my Lagrangian, khalas, my job is done. The next thing is to apply Euler-Lagrange equations, and I get my equations of motion. I give you this as an exercise. Okay? But one thing is important. I would like to know what is the canonically conjugate momentum to x in this case. What is this? I know what it is from here, remember? The old one? Okay? It's mv over root minus v squared over c squared. But now I have another term. What is it? Minus qa. Very interesting. Huh? Yeah. So A is the vector potential, when multiplied by the charge anyway, behaves like a momentum. It's like a moment. It's the moment. And in a way, it's not exactly the momentum of the field, but it behaves like the momentum of the field. It behaves like the momentum of the field. Okay? And this is what you have to, when you go to quantum mechanics, this is the thing that goes into h bar over I gradient. It's not this one. It's this one. Okay? We'll come back to this, inshallah, if you have the time later on, why this is important. So the vector potential is immensely important in quantum mechanics because it goes into the momentum. It is part of the momentum. Okay? So when you write Schrodinger's equation, p squared over 2m, that p there should include the vector potential. Okay? Forget it for the time being. We'll come back to it later. Yes. No, I'm not specifying any gauge. This one, I'm not specifying any gauge. No gauge. Did I speak? Huh? E and B? E and B are uniquely fixed. Okay? I'm not specifying any gauge. I'm not specifying any gauge. I didn't need to specify any gauge. Okay? Not yet, at least. I think this is off. I heard some noise, I don't know. It's okay? Okay, Shabab? So, as an exercise to you, or you can do it later if you want. This will give you this. And you know what F is? Okay? This will you Q E plus V cross P. These equations will give you these equations. But it's not trivial at all. It's not difficult, but it's not trivial. Okay? Clear? Any questions? So, we derived Newton's laws of motion from the principle of least action. We derived Lorentz force law from the principle of least action. What remains? Maxwell's equations. We'll do it next time. I'm talking about the classical physics now. Geodesics. Geodesic equation. Okay? Now, Now I have a free relativistic particle moving now in a fixed background of a gravitational field. So I'm not worried about the gravitational field, it is fixed. Okay? So in a way, I'm trying to find the Lorentz force law for a particle in a gravitational field. Okay? But the gravitational field is now fixed. It changed the metric of space and time. Now, how do we take care of that? In special relativity, where space-time was flat, okay, we introduced the space-time interval ds square to be eta mu nu, which was fixed, just one form, dx mu dx nu. This is for special relativity, flat space-time. When you go to general relativity, the way the gravitational field makes itself felt, it will change this metric. It will change this metric. Now ds square becomes g mu nu, which is now a function of x. What I mean by x here is space and time. Okay, the metric now is time as well as space dependent in general, but it keeps the same structure. That's our starting point now for general relativity. This is for special relativity. Okay? In special relativity, we define the action to be minus mc square, the integral, I don't remember what minus mc, the integral of eta mu nu, dx mu, dx mu. Okay? Clear? Now, what would be the action? It's exactly the same thing. But now eta mu nu gets replaced by g mu nu. Okay? So it's minus mc, the integral, square root, g mu nu of x. Let me remove this. We know it's function of x, okay? dx mu, dx mu. That's my action. The gravitational field is fixed. Okay? Gravitational field is fixed. Okay? What do I go from it? Yes.
What do you mean by the gravitational field is fixed?
I'm not changing the gravitational field itself. What I'm looking at is you know the Lorentz force law? I'm saying E and B are fixed. But E and B, they tell the particle how to move. Yeah, it's changing as a function of space and time, but once it has a certain configuration, and that's it. It's not, it has a certain configuration. Yeah, G will be a function of X, okay? But whatever that functional dependence is fixed, okay? Now I need to that's the only law of physics, by the way. That's the only law of physics you need. That's it. That's all you need. Okay? Everywhere. Quantum mechanics, classical mechanics, for non-dissipative systems at least. Okay, so let's do it. So it's minus mc delta, or if you want, delta root of g mu nu dx mu dx mu. Okay? And that should be zero. Should we do it? Should we give it to as a homework or something? Huh? I have to be very gone now. It's not difficult really. So what changes here? This will change, and this will change, and this will change. But the change of this and this are the same, so I get twice. Okay? And this will change. Okay? So let me, I wrote some notes here, so I cannot remember this. Okay. So, okay. So this is, I start from here. Okay? I start from here. So, what is, I change this, delta of this. Okay? So I'll have here, so delta ds square. Okay? So this is equal to 2 ds delta ds. Okay? You agree? Okay? What is this? This is just delta g mu nu dx mu dx nu. Okay? Okay? So what is this? This thing is, as I told you, this one. So first let me change g mu nu. So I'll get dx mu, but delta g mu nu is a function of x. So use the chain rule. So this is partial g mu nu partial x rho, okay, delta, yes, x rho, okay, plus, can you see in the back? Huh? Maybe it's too tight here. Plus, now I think, now I apply the delta to these guys, okay, because it's contracted with mu nu, which is symmetric. These also are symmetric, so I get twice. Okay, I change this one, keeping this one fixed, and then change this one, keeping this one. I get the same thing. So it is plus twice g mu nu dx mu delta dx nu. Okay? طيب, let me continue here. طيب. So my delta S is equal to what? You know, this is my delta S. So just multiply by minus MC, integrate, and this delta here, I can get it from here. Okay, what is this? So this is minus MC, the integral, 1/2 dx dx mu ds dx mu ds partial g mu nu dx rho upstairs dx rho, okay, plus g mu nu dx mu ds d delta x nu ds, the whole thing ds. Am I going too fast here, or? So what did I do? What is delta of the square root? Okay, it is 1/2 delta of this divided by this thing, right? But this thing is nothing more than ds squared, which is ds times ds. That's why I get the ds. That's the square root. Okay? This is what I did. Okay, derive this. So delta of this, which is this thing here, okay, divided by this thing. Okay? That's why I have this thing there. Fine. Now it's tensor algebra, ya shabab. I don't know whether you are interested in. It's only 2 or 3 lines, but let me not write the full thing down. If you're interested, you can come to me or you can do some other time. What you will get something like this. D square x mu ds square plus gamma, and I'll tell you in a moment this gamma is, okay? Let me put mu here. You get mu rho, and here I have, okay, dx mu ds dx rho ds. This is interval, huh? Or the property, 0. That's my geodesic equation. What is this gamma? Is something we call the Christoffel symbol. Okay, the Christoffel symbol. What is it? Gamma mu rho is 1/2 partial g partial x plus partial g partial x minus partial g partial x. Now you have to remember what symbol goes where. Okay? There is a trick about it, but I'm not sure I can remember it. Where is it? Does anybody remember what this Christoffel symbol is? I think is nu rho mu. So this will be here mu rho. So this is here mu nu, and here not mu nu. So this should be mu. Okay, mu is here. Nu, so the rho is left, and here is mu and nu. I think this is correct. Okay, so it tells you how the metric depends on position and time. Essentially, that's what it tells you. How the metric depends on position and time. If the metric is constant, like flat, let's say, okay, then all of this will be 0. Okay, and ds square will be just c squared dt square. Okay, c squared dt. Well, dt here is really the proper time. Okay, so c squared dt square, and you have d square x dt square equal to 0. What is that? D square x dt square equal to 0. What is that? That's the straight line. That's the straight line. And a free particle in 0 gravitational field, flat, moves in a straight line. That's what it is. Here it tells you how a particle moves in space, which has space-time, which has a certain metric. Certain metric that can be space-time dependent. This we call the geodesic equation. In later lectures, we'll derive it in a different way. More meaningful and more physically interesting. This is the straightforward way. Okay. Derive it later, inshallah, using a different way. Okay, so I've been talking for 1.5 hours. I don't know whether I made a point. There are Newton's equations of motion. There are Lorentz force law. There are geodesic equation using the same principle, which is the principle of least function.
Okay, next time we'll use the same principle to derive Maxwell's equations. I will flash, I will just give it to you. The gravitation field equation of Einstein. It's a little bit more. Okay? It's a little bit more. Just write it for you until you guys can derive it from. Yes, sir.
What is the motivation behind this principle of this action?
What is what?
The motivation behind it. Other than it gives correct answer, the same as the theories we already knew.
Yeah. I can give you the equations. Let me just come back. This is now the way physics is done. In QED, or QED is easy, but in let's say QCD, for example, or in, I don't know, some crazy theories, you start with the action. If you are lucky, and you know what the action should be as a function of your variables, dynamic variables, then you probably solve it essentially. The rest just write the all the Lagrange equations. Whether you can solve these equations or not, like in QCD, you cannot solve them. Okay? Out of luck. It's not a problem. It's not a problem. But you understand your problem. Okay? You understand? This is how things are done. But why? This gives you the wave equations for anything. That's as I told you, that's the only equation you need after S equals 0. But you don't have to know what S is and the functions of dynamic variables. Okay, in order to make sense out of it. Now, why is this better? But because it allows you to, it applies to everything, to the largest possible number of physical systems that you can think of. Conservative systems, at least, or non-dissipative systems. Okay, I don't know if you need a better argument, because it allows you to derive equations that are covariant and do not depend on the reference frame. That's the beauty. They have the same form in any reference frame. Even curvilinear, I mean, go ahead. Newton's equations of motion, the curvilinear coordinates. No, you can't. You know, you cannot even what the forces are. It's impossible. This allows you. That's the power. It's a very, very powerful. It works with particles, mechanics, not with fields, whether material fields or matter fields, I mean, or with electromagnetic fields. Okay? For any spin, doesn't matter. Okay? And it allows you to derive conservation laws, which, inshallah, we'll have time to talk about. So I call it famous Brothers theorem. So, if you have any questions, I'll be happy to answer them.
Who is the author of the research?
What is your question?
Who is the
author? The author? Oh, there's no single author, actually. Some people contributed a lot. It's a long history. It's not one person did the whole thing. No, it doesn't work like that. Okay, many people did a little bit of things, but the guy who tried to put it in more or less coherent form was Hamilton. And the name for it, another name for it is Hamilton's principle. Okay, but he wasn't the one who invented it in a way, because people is many people, Lagrange, you know, is one of them. Euler, another one that he did it for mathematics more than physics. D'Alembert is another guy. Many people contributed in little ways. Okay. Feynman in quantum mechanics, Dirac, all these guys, they contributed something. Okay. But some people come after a while and they synthesize the whole thing, like Hamilton did for classical mechanics, or Feynman did for quantum mechanics. And they give it a very finished touch. You know, looks very beautiful, something very nice, something very elegant. But the work is not so pretty. It's full of love. Yeah.
So upon the involved condition here that the action should be invariant under all transformations, right?
Yes.
Does this also apply for the Lagrangian?
No. Lagrangian is nothing. Well, yeah, if you want. You see, if you work in relativistic, you see, you write the action. In non-relativistic, you write it like this. This T here is not an invariant. So this cannot be an invariant. This is an invariant. But if you go to fields, this is for parking. For fields, this becomes a Lagrangian density, and this becomes now 4 volume. Okay, it's like dx dt. That's your Lagrangian. Okay, let me try to integrate here. This inner integral is your Lagrangian. Which is Lagrangian density times the individual volume. Integral.
So the Lagrangian density is invariant?
This Lagrangian is invariant. Lagrangian density should be invariant. Yes. Why? Because if I have this like that, this is a Lorentz invariant. And this is a Lorentz invariant, so this better be a Lorentz invariant also. And it is. But not for mechanics. For mechanics, L by itself, straight L, is not an invariant. Okay, it's not an invariant. Lagrangian density is. Any other questions?
Next lecture, we're going to go with that.
We derive. We do a couple of. I don't have a preset plan for this. Okay, we derive. I think it's good to derive Maxwell's equations of motion. We can say something about Einstein field equations. Okay, and then we can move on to quantum mechanics. Talk about path integrals. Okay, and how this can be used to derive Schrodinger equations of motion, more relativistic. And then from there on, we'll see what happens. We can talk about more. Quantum mechanics, more. It's classical, but as a prelude to quantum mechanics. Okay, talk about groups, and rotation group, and all that stuff. Okay. So this is the plan. I don't have a preset plan. Just we talk and people and ask questions. So what did we do today? 3 things. Use the principle of least action. Yeah, there are Newton's equations of motion. That's the whole of classical mechanics. Okay. Then we derive the Lorentz force law. That's half of ENM. The other half is Maxwell's equation. Okay. We derive the geodesic equation. That's half of general relativity. The other half is Einstein's equation. It's a lot. Quite a lot. But we have homework to do. Don't forget that. Okay, Shabbat, if there are no other questions, just thank you for yes. Okay, thank you for being here, and I hope you enjoyed it as much as I did. Learning just like you, everybody, and I hope to see you again.